Hey again, everyone. Welcome back to the Joy of Coding at Portland State University. In the first part of our discussion of source code management, we learned some fundamental concepts and saw how the Git tool can be used to version source code as multiple people modify it over time. We learned about repositories, revisions, and branches. If you haven't watched the first part, I encourage you to take a look at it, or thumb through the slides on the course's website, before diving into this screencast, which focuses on more advanced concepts in source code management like version numbers, tags, and distributed version control. Now, another important part of source code management and software release management is the versioning of software. And whether you're releasing, an end product like an app or just a library that other people are using in their software, it's important to convey information about the version of the software so that people know what they're getting and can have a quick understanding of the amount of change that they should expect from one version to another. A kind of de facto standard that has emerged over the last couple of years is something called semantic versioning. And we've all seen this, right? This is where you have a version that has three components, a major.minor.patch format. And what you might not realize is that there are some rules or some guidelines for how you define the major or the minor and the patch. So as you're deciding, what version should I use for my software, if the changes in that version are just bug fixes that don't really affect any external semantics, you're not changing the API, then all you need to increment is the patch version. So going from version 4.1.0 to 4.1.1, when you fix a simple bug, basically make an internal change that doesn't impact external behavior, great. That's when you just increment the patch. That's the the rightmost versions or the smallest version. Now, maybe there's a larger change that you're making. Maybe you're adding some new capabilities, adding new methods to call in your library, but haven't really broken anything else and haven't broken anything existing. That's when you'll want to increment the minor version. That's the second number in the semantic version. So, for instance, maybe you have an API that's still there, but you've deprecated, saying, I don't want anybody to use it going forward, I'm going to remove it eventually. That's a good motivation for incrementing the minor version. And of course, when the minor version is incremented, the patch version reverts back to 0. So you go from version 4.1.1 to version 4.2.0. Finally, if you make a big change to your API, you either add something new or significant, or if you make a breaking change. Maybe you've finally deleted that deprecated API that you've told people are going away, or you purposefully realize there's just something wrong or insecure about the current API. That's when you issue a new major version of your library, of your software. And so, semantic versioning provides these guidelines so you know how to interpret the changes, but it also then provides an ordering or precedence for the versions. So basically, version 1.0.0 is less than 2.0.0, and then 2.1.0 is greater than that, and then the most recent one of all is 2.1.1. And because of semantic versioning, tools like Maven and really anything that works with versioned artifacts know how to find the latest and know when an upgrade's available. So this discussion of software versioning brings us to tags in Git. So what a tag is, it allows you to associate a human-readable string with a version. Right? A version is that hash number, which is like big and ugly and hard to remember. But sometimes you want to give a well-known name, something you can share with someone else, to a particular revision. And that's what tags are for. So the way you create a tag is with the git tag command, and you use the -a option for adding. And so that first example there creates a version 1.0.0 tag from the current revision, from the head revision. And just like a git commit, you can have a -m for a message, so you can provide a message along with the tag. And so that'll create a 1.0.0 with tag with the message initial release with the current revision. You can also go back in time and tag older revisions. Maybe you had a beta release off of a previous revision, and so you can tag that as version 0.1.0. And the way you do this is you provide a uniquely identifying prefix of the commit hash. When you issue the git tag command with no arguments, it prints out the list of all available tags. So tags not only provide just good history information, you can also, because they are essentially an alias for a revision, you can create a new branch from a particular tag instead of the commit hash. So you can say git branch, and you can have a new branch that is named v1.x.x from the v1.0.0. And so now you have a code branch that was created from your source code at a point in the past, because maybe there have been some commits since version 1.0.0. And now you can do things like fix bugs, or maybe go back and do some archaeology, or try an experiment with the older code base. So this is a good way of, again, being able to issue updates or bug fixes to older versions of the software. One of the interesting properties of Git is that a full copy of the repository is maintained on every developer's machine. Previous revision control systems only maintained either a subset of the code, or didn't have all the metadata, or had to go back and forth between a server and a client in order to maintain everything. While that had some nice benefits, like there's fewer files on your local machine, you had more network bandwidth. It didn't really work out very well. It meant there was sort of a primary copy of the repository out there, and so if something happened to that, everybody was dead in the water. The decentralized approach of Git really made it more resilient, and in this day and age, disk space is so cheap that it's not a concern even for the largest of source code repositories. So Git offers distributed version control, which really enables people, no matter where they are, whether they're sharing a machine or on different machines or they're in different locations, to collaborate on a code base and keep everything maintained with good integrity. So when you want to make a local copy of a repository that is maybe hosted someplace else, there are a couple of Git commands that you can use to do so. So by saying git clone, and you give clone a URL, what this will do is we'll create a copy of the repository referenced by that URL on your local machine. And it basically retains a connection back to, as I'll say, an association. It's not like a network connection. It's more like an association back to the repository at that URL via a remote repository called Origin. So the whole idea is that you have a clone on your local machine, and the origin of that clone resides someplace else, often that URL. If you want to learn more about the remote repositories associated with your local repository, you can say git remote. And if you use the -v option, it'll give you the URLs for that remote repository. You use this most often with GitHub. So GitHub is a repository of Git repositories that is available on the internet. And as you'll see, as you've probably already seen in this course, we clone repositories from GitHub to our local machines, and we work with them locally. And you can then learn what remote repository your local clone came from by saying git remote -v. So instead of using git init to create a new repository from scratch, you can get an existing repository by cloning it using git clone from some URL. Now it's a Git repository, and so you can add new files, you can commit things, you can look at the history, but there are a couple of commands that then allow you to interact with the remote repository so that you can get the changes that other people have made and contribute your changes back to the shared repository from everybody else. So git pull, what it does is it integrates changes made in the remote repository into the local one. It's a lot like a git merge, but it's working with a different repository as opposed to a different branch in your current repository. So git pull will, let's say your repository is currently working on the main branch, and so what a git pull will do is it'll go consult the remote repository and say, hey, have there been any changes since the last time I pulled in changes? And if the answer is yes, it'll go pull those changes down and add new revisions to your local repository. So you'll get those changes along with their commit history. Similarly, a git push will send committed changes off to the remote repository. And so maybe you've made some changes locally and you want to contribute them back to the shared repository and the remote machine, like in GitHub. That's what git push does. Now, again, just like merging branches, if there are conflicting changes, so maybe someone has pushed changes to the same line in the same file that you've changed locally, you'll get conflicts, and you'll have to resolve those conflicts before the push or the pull will be entirely successful. And so then between branching of repositories, between remote and locally cloned repositories, Git enables this distributed version control of software, which is the most powerful tool we have right now to do this. As you can imagine, things can get a little confusing, as depicted here on the image, where yes, you can have multiple people working on multiple branches on clones and committing and pushing things back. But this really allows people to work asynchronously and has enabled people to go very quickly. And as long as you are pushing and pulling often, are aware of what other people are doing, Git really makes this surprisingly easy. And I think it's fair to say that in a few more years we'll look back and we'll see how Git has really improved the lives and allowed so much software to be created. It's really powerful stuff. So as I was saying, Git repositories are usually hosted someplace, especially if you're an organization, a company, nonprofit, some enterprise. They'll have or basically a repository of repositories where all of the Git repositories live. This will be the primary copy. This is good. So there, because it can provide that access while still having good IT practices, like have it being backed up and having authentication centralized, all kind of good stuff like that. And also, many of these systems provide the ability to view and comment on the code without making a clone, which can be very convenient for people who either aren't developers or just someone who doesn't want to have to get a whole copy of the code and then open it up in their text editor to be able to find stuff. In this course, we use GitHub.com to provide hosted Git repositories. GitHub's cool because just beyond providing basic Git support, it has some extra facilities to enhance collaboration. So in GitHub, you can create what's called a pull request, which allows you to request that changes from a branch that you've been working on be integrated into the primary branch of the repository. And as part of that request, you can have a conversation with other people about the changes that you've made, and so things can get approved or denied, and suggestions can be made. It's really good stuff. GitHub also allows you to what's called fork a repository into your own organization or personal space. So maybe there's a repository out there that you want to start experimenting with, and so you can make basically your own copy of it in GitHub, which then you can clone locally and work with. GitHub also has the ability to search for information in repositories, and also has some tools for doing project management. Things like having a wiki where you can capture documentation. You can have issues for managing requests for change and other work, things like that. Additionally, GitHub provides some command line tools that provide advanced workflows and really things that are customized for GitHub, which is nice to be able to do from the command line. And then also some nice applications for the native operating system for just making it easier to work with Git and GitHub. Here's how a pull request works. You'll probably see it at some point in your career if you haven't already. So again, pull requests provide a nice user experience for proposing changes from one branch into another. Usually it's the main branch, or whatever primary branch that is. So the developer who wants to make the change pushes the changes up to a branch in GitHub, and then the developer creates a pull request. And we can look at it in a class. There's a nice user interface for selecting which branch you want to merge from and the branch they want to merge into. It's not unlike making a transfer at your bank between two accounts. Once that pull request is created, other developers can weigh in on the change, and depending on how the repository is configured, an approval might be required in order for the change to go through. In addition to a review by people, GitHub also has the ability to run continuous integration on the change, and so then it'll automatically build the code, run the tests, really whatever the developers want it to do, to determine whether or not the changes cause problems. So it'll let you know if it causes unit tests to break, or if the code no longer compiles, or it maybe there's some code analysis that you do. Maybe you've inadvertently introduced an insecure library into the ecosystem, or you have code that is likely to break or introduce a security flaw. Once the changes have been improved based on all of this feedback, they are easily merged into the target branch, and at that point, the development branch can be deleted. It's a really nice end-to-end workflow for integrating changes into a branch. So here's some things that I hope you've taken away from this set of slides. I hope you've gotten to see Git and what it can do. And there's a reason that's the leading tool for working with distributed source code right now. It's really quite powerful. It is very battle tested. Tens of thousands of people have used it over the last probably almost 2 decades that it's been around. And it solves the problem really well. Definitely a leading solution right now. And the way that Git enables people to collaborate is that it gives them this well managed and well accounted for history of the changes that have been made, so that you know what you've changed, you know what others have changed. And as changes come into the system, it's very good about reconciling them in ways that make sense for the developer. Most of the time, all the changes flow quite nicely, but if there are conflicts in changes, Git detects it and brings it to your attention quite easily. And a key feature of Git that enables concurrent development are branches. Branches allow developers to work independently of other changes, develop things in isolation, and then contribute them back. And when Git is paired with GitHub, what you end up with is a great system for doing distributed version control and an authoritative source for your repositories. And Git supports all of this with the push and pull commands. There's lots more to learn about Git. Here are some resources that I found helpful and I think might be helpful for you. Everything ranging from the book on Git, some nice tutorials, and then also more information about trunk-based development and semantic versioning, if you'd like to read more about those. So phew, we made it to the end. So that was a lot. And I hope you enjoyed learning about Git and source code management. Hope you have a better idea of how Git can help you more effectively develop code over time, especially as you collaborate with others. Thank you for watching, and I look forward to hearing about how you apply what you learned today in the joy of coding here at Portland State University.